All right. So we left off yesterday. We saw some formulas for the inverse. And we're going to go through it and at least do one example and kind of tie all of these ideas together. Properties of determinants we also saw, namely that determinant is multiplicative, and we learned determinants of elementary row operations. And so as we kind of saw, maybe we'll pull up the notes from yesterday. Hopefully we have a geometric intuition of what determinants are. They compute volumes for us. And in some sense, you should get the idea of, well, what's going to happen if our determinant is 0? What does that mean? Well, that means it has a 0 volume. Right? So for example, if I have 3 vectors, but they're not linearly independent, then the directions they go to, in some sense, it means one of the vectors is in the span of the other 2. And if one of the vectors is in the span of the other 2, then even though we have 3 vectors, the span of those vectors is only 2-dimensional. So if we try to compute a 3-dimensional volume when it's only 2-dimensional, its volume is 0, right? It's like trying to compute the area of a line. Well, it has no area. It just has a length. So that's what a 0 determinant means. So intuitively, you should also kind of think, well, if that volume in these parallel pipettes that are formed by these 3 vectors, if the determinant is non-zero, well, then I have a full volume. In other words, we're transforming the plane. I don't think we ever drew a 3D picture. But in other words, we're transforming the plane with a different scale under this transformation represented by the matrix. And we're not destroying anything. We have a full volume. In other words, and since all the processes are linear, if I have a non-zero determinant, we can undo that operation. We can go from our slanted grid back to our rectilinear grid if we wanted to. So intuitively, that's kind of our geometric reason why if a determinant is non-zero, we can find the inverse of a matrix. And vice versa, if the determinant is 0, well, that means I'm killing off certain dimensions. And without being able to really keep track of that, we can't sort of undo. If I multiply a number by 0, and now I just see the answer is 0, well, how do I undo that? How do I recover the number we started with? We can't. It's kind of the same thing with these determinants. It's kind of like if I kill off a dimension, and now I'm just looking at the image, and the image is 2-dimensional, and I know it came from a 3-dimensional space, it's really hard to determine which specific dimension we killed off, because that one dimension could be angled in different ways. It could have different linear combinations. There's a lot of different ways that dimension could be angled and correspond to the other 2 dimensions that we don't know which specific vector representing that would have been killed off. So we can't undo a matrix when the determinant is 0. So we saw our Laplace expansion. And then we also saw all of our elementary row operations. And so these elementary row operations are gonna be huge, right? They don't change the determinant except for the first 2. And we've seen most of the processes we've done are of type 3, right? We want to add scalar multiples of one row to another row. Those are almost always our first steps. And so that doesn't change the determinant at all, meaning I can perform those row operations on my matrix without changing the determinant. So we're going to start doing that a lot today. And then you do have to keep track, if we do have to scalar multiply a given row or switch 2 of the rows, just keep track of how many times you're doing that, because that will adjust the determinant. But that's easy enough to undo. So for example, if we multiply one of the rows by a half, what's that going to do? It's going to multiply the determinant by a half, which means in the end, to undo that, we just multiply the end result by 2. And then we will take a look at some of these other ones. Like if A is a triangular matrix, then the determinant of A is a product of diagonals. So I'm going to take advantage of that. It's a big reason why we want to do row reductions first. Get it into, we don't even have to get it into a row reduced form, but close to a row reduced form where maybe all of the first entries don't necessarily have to be 1. As long as we get it into a triangular matrix form, taking the determinant from that is going to be really easy. And then let's see. So we'll have to get into the applications today. And then it'll be the applications of finding a new formula for finding inverses of matrix and Kramer's rule, and then maybe this polynomial stuff. And then also, depending on how long that takes, we can get into spectral theory. I was looking at the material, and the material is actually not a lot to get through. But as we get into some of these computations, we've seen a lot of them do take a long time. So this was I'm just going to continue from the notes from yesterday. This is where we left off. So 727, we've got applications of determinants. So we left off with this matrix, and our goal is to just compute the determinant. And it's a 4x4, so it might take us a little while. So our first step is going to be to row reduce. You could just straight up compute using Laplace expansion, right? Either expand upon a row or a column, whichever one looks nice, and then compute your minor matrices. But that's going to be, we could do that, but remember that as soon as I have one minor matrix, now that minor matrix is a 3x3. And now even in that 3x3, we have to expand and use Laplace expansion. So iteratively doing Laplace expansion twice, it gets really complicated, really hairy with the algebra, and you got to be very mindful of all your parentheses and all the terms you're grouping. And it's almost more computations than what it would be if we did some easier techniques in terms of row reducing. So let's actually row reduce first, especially since we have these ones, or at least that one there. And then like we don't have any zeros here. That's the other thing I'm looking at, is like when we want to compute a determinant, if you have a lot of zeros in a given row or column, it makes things quite nice, because then the determinant, a lot of the terms you don't even have to compute, because it's going to be 0 times that minor matrix. But no zeros, all a bunch of constants. So let's go ahead and row reduce. So what are we going to do? Let's go ahead and keep the first row as it is and eliminate all the entries in the first column. So let's make all those zeros, and we can do those all in one step since they're not going to affect each other. So we want -5 row 1 plus row 2. So that'll give us a 0 there. We'll have -10 plus 1 is 9, negative. We'll have -15 plus 2 is -13. We will have -16, -5. So -20 plus 3 is -17. Not nice. Then we've got -4 row 1 plus row 3, 0 there. -8 plus 5 gives us -3. -12 plus 4 gives us -8. And -16 plus 3, -13. We've got now -2 row 1 plus row 4 gives us a 0 in that first entry. -4 plus 2 is -2. -6 minus 4, -10. And then -8 plus 5 gives us -3. Everyone with me? All right, so how do we do these other ones? Let's see. I kind of hate this 9. Not easy to use the 9 to to eliminate any of the other entries in the other row. So I'm going to eliminate that 9 first. So we've got 1, 2, 3, 4. So what I'm going to do, we kind of want to do the process of row reduction. You can flip rows. I'm going to hold off on that. So normally we like to keep that entry solid, keep it as a non-zero, and then try to get the zeros below. We can kind of finagle that a little bit and just keep, really, let's keep the first row the same. And now let's get zeros in 2 of the other columns. And this one's going to be fairly easy to get a 0 since we have a factor of it down here. So if we do, for example, -3 row 3 plus row 2, we'll have a 0 here, and then that'll give us a +9 and give us a 0 there. So that'll give us our 2 leading zeros. And then we can flip this row down maybe later. And of course, we'll have to keep track of how many times we need to do that for the change in the determinant. So, and the other thing you could do is keep track of the steps. So for example, let's call this A. Let's call this one A2. And then maybe as a note, since all of the row operations didn't affect the determinant, we know that the determinant of A2 is equal to the determinant of A1. So just as an aside, maybe we'll put that there to keep track of our work. Okay, so we had 3 times row 3 plus row 2. So that'll give us a -3. So that'll give us 24 minus 13 is what, 11? And then -3 times row 3, that'll give us 39 minus 17 is 22. Is that right? Yeah. So shout at me if I do any of these works wrong. And then maybe we'll keep, just for the sake of order of operations and clarification on the work. So if we call this equal to A3, and then we know that the determinant of A3 is still equal to the determinants of A1. And I guess that, let's make our A1 the first matrix there, if I didn't write that. The reason I wanted to do that is because now I actually want to eliminate that 3. It's not easy. Of course, now we got a 2 and a 3 here. And I want to do like 1.5 times that to eliminate the other row. 1.5, again, we're getting into fractions, which start to just complicate the arithmetic even more. But luckily, 1.5 is an easier fraction than some 2/9 or something like that. So we've got our 0, 0, 11, 22. And so now for this row, our third row, we want to do -3/2 row 4 plus row 3. And now let's see what we get. We'll get a 0 here, a 0 here, and 3/2. So we'll have -3/2 is 10, is 15, minus 8 gives us +7. And then this one, unfortunately not nice. We'll have -3/2 times 3 gives us 9/2 minus 13. So 13 is 26/2. So 9 minus 26 is going to give us what, -17/2. And then our bottom row we kept. I do that right? Anyone check me on that? 9/2 minus 26, 26 minus 9 gives us 17. Yeah, that sounds right. Unfortunately, we got that fraction in there. Okay. Any easier things we can do? So we want to try to eliminate stuff in this row. And I think the easiest thing is going to be to factor things out. So now we're actually going to change the determinant. So why don't we go ahead and reorganize our matrix? And so this is A4. No debt change. So far we are exactly the same as our original determinant. But now what we're going to do is bring up this -2, -10, and -3. So that gives a negative. We are going to have a 0, 0, and then I'm going to pull out the 11 from this row. So it'll be 1, 2. And then 0 minus, sorry, wait, I moved that row up. I need this row then. So 0, 0, 7, and 17 halves. So this is our A5. How did the determinant change? So I know that the determinant of A5 is going to be negative. So we flipped 2 of the rows, so that'll give us that negative. And then the other thing we did was multiply one of the rows by 1 over 11. So flipping the rows gives us a negative. And then multiplying one of the rows by 1 over 11 gives us that 1 over 11 factor, right? So those are the operations. If we had those elementary operations applied to, say, A4, that's how our determinant equation would work out, because we could compute the determinant of those elementary operations. And so the two that change the determinant give us that negative 1 over 11. And now, nicely enough, this third row has a 1 in it, so we're just going to have 1, 2, 3, 4, 0, -2, -10, -3, 0, 0, 1, 2, and then 0, 0, 0. So we are taking -7, row 3, plus row 4. So -7 gives us -14, which is -22, or -28, plus 17 gives us...
Wait, shouldn't it be a negative 17 halves?
Did I miss a minus sign? I did. Thank you. Good. Okay, so -7 times, that gives us -28 over 2. Minus 17 gives us -45 over 2. And this is our A6. And again, determinant of A6 should equal the determinant of A5. So no changes there. And that's going to be -1 over 11 determinant of A1. So kind of hand in hand, like we're keeping track, of course, of the row operations, but then we're keeping track of how that's going to affect our determinants. Because now, well, let's go through this process. We listed as a theorem yesterday that if we have a diagonal matrix, then the determinant is just going to be the product of the diagonals. And the proof of that is easy enough to figure out by example. So now how do we compute the determinant of A6? We expand upon the first column. So the first step in the Laplace expansion is going to be, we're going to take this 1 and then now times the subdeterminant. So it'll be 1 times the determinant of 2 minus 10 minus 3, 0, 1, 2, 0, 0, negative 45 halves. But then if we expand upon the first column, what are the next entries going to be? It's going to be, sorry, it'll be a negative minus 0 times whatever subdeterminants. Actually, here, let's just write it as times our minor. What's that one going to be? 2, 1. And then, of course, it'll be plus 0 times the minor of 3, 1, and then plus 0 times the minor of a 4, 1. So hopefully everyone can see that's how that works, right? We would go down, and now the minor, it's going to be that coefficient, 0 times the minor matrix that remains. But since it's 0 times something, we're not going to have to compute. Likewise, 0 times the net resulting minor gives us 0. So we don't really have to compute those. And now we still have to compute the determinant of the 1, 1 minor. So this lower block here. And now what do? We expand upon the first column again. And so we've still got this 1 out here. And then now how do we do the determinant? Well, it's going to be our new 1, 1 entry, so minus 2, times the determinant of the resulting minor matrix. And then again, from that matrix, we're going to have minus 0, expanding down the columns, times the minor. I don't know if I want to call that A. Let's call it B. Let's call this guy B. Of 2, 1. And then, of course, plus 0 times the minor of B, 3, 1. The zeros will kill whatever those factors are. And so we're just going to have 1 times negative 2 times now this determinant, which we can compute. 1 times negative 2 times, and of course, what's going to happen? It's going to be 1 times negative 45 over 2. And then minus 2 times 0 is still going to give us another 0. So all in all, 1 times minus 2 times 1 times negative 45 over 2. So not too bad. We get 45. Now, this was, of course, the determinant of A6. And so our 45 is going to be minus 1 over 11 times the determinant of A1. So the original one we started with was A1. So all we have to do is multiply that times negative 11. What's 45 times 11? 450 plus 45, so 495. Equals the determinant of A1. So, question in the chat: how many row flips determine what sign? So each row flip is another multiple of negative 1. So in our process, we only flipped 2 rows. So going here, we flipped these 2 rows. So this would be P24. Gives us 1 minus sign. And then here, we had 1 over 11 times row 3. And so that adds that factor of 1 over 11. So this is kind of how we see everything tie together. We were applying our row reductions first, and then that makes our determinant much, much easier. So it's going to be up to you, like when you go about, if you have to compute a determinant 4x4s and bigger, sometimes it's easier to do row reductions first. And again, you don't even have to do all of the row reductions. You didn't have to get all the way to all of these zeros, especially if some of the numbers were looking messy. Even getting started with, a 1 with a lot of zeros below it and a 2 with a lot of zeros below it, we could have started computing determinants with Laplace expansion, and then where would we have ended up? Computing a determinant of a 2x2, and even if this was non-zero, it wouldn't have been too bad. So you can do them, trying to figure out your own techniques of, depending on the matrix, of how to go about computing these determinants most effectively. And again, like if we start with a matrix with a lot of zeros, sometimes it's easier to find just a row with a lot of zeros and to start with that. And then just go straight into determinants. So let's get into some of these applications now. So determinants give us a formula for the inverse, which is kind of funny when you first learn it. Because in all honesty, it looks way harder, and it kind of is. This formula that we're about to derive for the inverse, it's much harder to come up with than coming up with the sequence of elementary row operations to derive an inverse. For like 2x2s and 3x3s, determinants are fairly useful. You can compute the determinants fairly quickly, so you can kind of tell, at least from the determinant, whether or not it's invertible and get immediate information. But actually computing the inverse, like if you compute a non-zero determinant, then you have to compute the inverse, can take some work. So let's see how we go about doing that. So we need a few tools. So if we let A be an n by n matrix, then we call the cofactor matrix which we simply denote cofactor of A, is going to be the matrix of all the cofactors, or the minors. So the book kind of uses different terminology. We call the cofactor of Aij. Or did we use that? I'm confusing my own terminology between the cofactor and the minor. The cofactor includes the sign, yeah? Right. So we want to compute our cofactor, so the determinants of the Aij minor, along with the sign, so -1 to the I plus j. So essentially what we're doing, in our 1-1 position, we compute the determinant of the 1-1 minor, get a value for that, and then put that into the position 1-1. In position 2-2 is the determinant of the 2-2 minor. And then we compute the adjugate of A, which we denote Adj of A, is just the transpose of the cofactor matrix. So the cofactor matrix, first thing to compute, and then all you got to do is take the transpose. And our theorem is that for any square matrix, that A times the adjugate matrix of A is going to be the same as the adjugate times the matrix A. In other words, a matrix will commute with its adjugate And moreover, it's just going to be, the result is going to be the determinant of A times the identity. So whatever value you get for the determinant, if you list that same value all along the diagonals, then that's what this multiplication will give. And so moreover, so actually we should say the determinant of A is non-zero if and only if A is invertible. So we mentioned this yesterday. This is a more formal statement of why. And moreover, the inverse then is going to be 1 over the determinant of A times the adjugate. So this is kind of a lot. I want to go through the process maybe a couple times. There's 2 examples that we want to look at. And when you first see it and first do it, it's kind of like, well, why are we doing this, right? We have the formula for finding the inverses by keeping track of row operations, right? If I have in a matrix, we can append by the identity, do some row operations until we get an identity on the left side, and then whatever matrix on the right end results is our inverse. That's actually pretty quick, pretty easy to do, pretty straightforward. This, not as straightforward. So let's see an example. Let's see how it works. And our matrix A, let's just do a 3 by 3. A 4 by 4 would be a pain. So the first thing I'm going to do is compute the determinant of A. And I'm actually going to expand. You guys want to do the middle row or middle column? Any preference? Let's do the row. So what are we going to have? We've got to keep track of our minus signs. So since we're starting not at 1, 1, we're starting at 2, 1. We're going to have a minus sign there. We'll have a 3 times the determinant of the resulting minor. So we'll have a 2, 3 and a 2, 1 there. Plus 0. And then a plus to keep track of the minus signs, minus 1. So we're going over 0. And then now we have a 1, which is in position 2, 3. And then the coefficient is 1. And then the resulting minor matrix is going to be 1, 2, 1, 2. Computing our determinant, or the 2 by 2 determinants now, we'll have a minus 1 times a 3 times 2 minus 6, and then 0 and 0 if we compute that determinant. Of course, hopefully everyone can see that those rows are not linearly independent, meaning the determinant should be 0. And if you compute it explicitly, of course, we'll get 2 minus 2. So we'll get negative 4 times negative 3. Determinant is 12. That's the easy part. Now our minor is going to be a little more complicated. So let's rewrite the matrix here. One, 2, 3, 3, 0, 1. Did I have a minus 3 here? Or was that a mark? I think that was a mark from me doing that. That was a positive 3, yeah. Be careful with stuff like that. Easy to confuse your own writing, especially if you're marking your procedures. Okay, so here's our A. We want to compute the cofactor of A. So what's going to go here is going to be the determinant of the 1, 1 minor times a plus or a minus sign. So maybe we can do some scratch work and then I'll move through it quicker. But just to kind of write it out, our cofactor of 1, 1 is going to be our determinant of this matrix. So what results after removing row 1, column 1. And then, of course, we're going to have a minus 1 to the 1 plus 1. So determinant of that is going to be negative 2 times positive 1. So we'll get a negative 2 there. We got to do that for each position. So our cofactor 1, 2 is going to be minus 1. Of course, to the 1 plus 2 will give us a minus sign. And then 1, 2 is our top middle entry. So we will have the determinant of 3, 1, 1, 1 there, yeah? Yeah. So it'll give me 3 minus 1 is 2 times a negative gives us another negative 2. And then our cofactor 1, 3 will give us a positive 1 times 3, 0, 1, 2, our determinant. So that'll be 6 in that position. So we got to go through this quite a bit, but I mean, you don't have to write it all out. The numbers get fairly easy to do in your head. I would say be very careful if you're doing a computation like this, since there are a lot of computations themselves to do. Pretty easy to maybe miss a minus sign or something. So let's try to do 2, 1 now. So 2, 1 is going to have a minus sign associated with it, and we'll have 2 times 1, which is 2, minus 6 will give us negative 4 times the minus sign will give us positive 4. This entry will be positive times its determinant, so 1 minus 3, negative 2 there. And then this entry will be negative times the corresponding determinant. So the determinant is 0. And then down here, this is position 1, 3. So the sign is going to be positive times the determinant. So that'll give us 2. And then now this one will be negative, and so that'll give us 1 minus 9, so negative 8 times a negative will give us positive 8. This one, positive, we're in position 3, 3. Positive sign times the determinant is a negative 6. Everyone with me on that? And so now our adjugate matrix is going to be the transpose of that. So just make the rows and the columns. So first row becomes the first column. Second row becomes the second column. Third row, third column. Of course, the diagonal doesn't change. And so this means that our A inverse is, our determinant was 1 over 12. No, 2, minus 2, 8, 6, 8, negative 6. So if you're going to have a matrix like this, I'm fine with you guys leaving constants out front. I would say try to simplify it as much as you can. So we can distribute this 12 in the matrix if we want. It's almost messier that way because then you got to write a bunch of fractions. One thing you should notice is that all of these terms are even, at least. So maybe we just pull in a factor of 2. So if I leave a 1/6 outside of the matrix, multiply all the elements times a half. So -1, 2, 1, -1, -1, 4, 3, 4, and -3. So now all the entries are co-prime as a set. There's not a common element I can factor out. And then I'm just going to leave the inverse like this. For me, this is kind of the most simplest form to look at, right? I don't have to write a 1/6, the 1/3, and simplify any of those numbers to fractions. So now we want to check. Let's check, make sure we did our work correctly. We did a lot of computations there. A lot of them are pretty quick, especially these 2x2 cofactors. Not too hard to compute these 2x2 determinants in your head. Be very careful, though, with eyeballing it. You know, if you kind of just look at the wrong row or column and then see the wrong resulting 2x2 and compute the determinant backwards or something, real easy to make mistakes. So if it helps, write it out. Let's compute the product, at least in one direction. So we had our A inverse times A was 1/6 times our A inverse -1, 2, 1, -1, -1, 4, and then 3, 4, -3. And then A was 1, 2, 3, 3, 0, 1, and 1, 2, 1. So this is the reason why I left that 1/6 out. If we want to actually compute these and check to see if we did our inverse correctly, for me, it's almost easier to multiply the whole numbers together. And then if the result is 6s on the diagonal, we multiply that by 1/6 and we're good. So let's keep the fractions out of it just to make our brains a little easier for the arithmetic. And so now we're going to do these dot products, right? Our matrix multiplication, row 1, column 1. We will have -1 plus 6 plus 1. Good. We get a 6 there. And the other thing, since we're looking, we expect to get the identity matrix, which means all of the entries should be 0 except for the diagonal. So it doesn't matter what the scaling factor is. And so it's almost easier to compute the whole numbers. And we're expecting to get 0. So let's do row 1, column 2. We'll get -2, 0, and +2. Gives us 0. And then our third entry here, we'll get -3, +1, and +1, or +2 and +1. So 0 again. -1, -3, and +4 gives us 0. So far, so good. We've got -2, 0, and 4. Uh-oh, did we miss a minus sign somewhere? Should get 6, right? Did I add in an extra minus sign?
No, it's just 4 times 2, so it's 8 minus 2.
Ah, I can't do math. Thank you. Right. Right, 4 times 2. For some reason, I was doing 4 times 1. Good. So we get our 8 minus 2 gives us 6. We've got 3, -3, -1, and +4 gives us 0. We've got 3 and 12 and -9. So, wait, did I do that right? So 3 and 12 and -3. Uh-oh. Did I do the bottom row different, or am I mathing wrong again? Let's see. So what are these other rows? So that'll give us 6. That'll give us -6. So we get a 0 there. This will give us 9, 4, and -3. Uh-oh, something's wrong with these last entries. Okay, so let's go through how to kind of error check. We can pretty much guess that the first row is correct. So since this first row, we got 6, 0, 0 is good. Second row is also good because we got 0, 6, 0. The third row, something wonky is happening. We have a 3 times 1, which is 3, and then a 4 times 3. This 4 may not be correct. So this middle entry is fine, which means this bottom row times this middle one should give us a 0. The problem is we know this is for sure A. That's the matrix we started with. So we got to kind of error pick what's going on with our A inverse. And so this 4, well, we don't get information about this 4 in the middle column. This 4 could be any number, and that middle column is still going to be correct. The 3s may be wrong. Maybe we'll check the last entry again. We'll get a 3 times 3 is 9, and a 3 times -1. For some reason, I think this 4 might need to be a 0. Let's go back and check that. So it's this entry here and how we computed it. Our cofactor of A, and this is 3, 2, should give us a -1 times now the determinant of 1, 3, 3, 1. Yeah, exactly. So that'll give us a 0 there. Everyone see kind of how I got to that? So if this entry, let's use red so we can correct ourselves. So that should have been a 0, 0.
Wait, isn't the determinant of that 1, 3, 3, 1 still -8?
Yeah. Maybe I put them out of order. It is -8. Wait a minute. I was seeing the same rows and columns and then thinking maybe if it was 1, 3, 1, 3, we'd get 0. Yeah. -8 times the negative, so that should give us a +8. Yeah. And then when we factor out a 2, that should give us a 4. Unless I copied one wrong. No. Okay, so maybe we check the other entries. Because if that were a 0, it would get 6 minus 6, which would give us a 0 there. If this were a 0, it would give us a 3 minus 3, which would give us a 0 here. And it would give us a 9 minus 3, which would give us a 6. So the problem is that if we have an inverse, it's unique. So if I put a 0 there, the fact that it gives us the correct result bothers me. Well, this was our original matrix. We need this entry, and we have 1 times 1 minus 9 gives us -8 times that cofactor. Okay, I mean, maybe we check the other ones. If we do here.
Mackenzie commented that you should check the transpose, and I think that would be right, because if there was an error when you transposed it, then the middle entry on the bottom would not be a 0 when it should be.
Yeah. So we got to go back even further.
The cofactor matrix is right.
Cofactor. That's what we need to do. So it should be 0 because that 0 should go there. Thank you. So that should be a 0. And that number is correct. So good. Thank you, guys. And that's what can happen, right? Cofactor is right. I just forgot to take the transpose. I kept that 8 in the same position and put it also in that position. Good. Good. Error checking. So we do get a 0 there. And then we'll get a 0 here and a 6 here. Thank you, guys. And this is, of course, a good way to check your work. Yeah, cofactor matrix was correct. I think I was looking at the steps wrong. I should have checked the transpose because that was what gave us that position. Good. So we got our inverse. And again, you kind of saw there's a lot of computations going on there. Not too bad. I don't know how you guys think if it's better than row reducing doing that way or not. I think there's a little more room with error with all these separate calculations you got to do, whereas row reduction is pretty straightforward, but it almost seems about the same to me, at least for a 3x3, because of course row reduction is you got to eliminate 6 entries, and then you got to go in reverse to eliminate the upper diagonal entries. Here, of course, we've got 9 entries to figure out for the cofactor matrix. Transpose is an extra step. So I don't know, maybe this method seems a little bit longer. But the question is why is it useful? I think if you're a computer science person, the nice thing about the formula is that it is a direct computation. It is a direct algorithmic process. Whereas row reduction, not so much. It's kind of hard to program a computer to do row reduction because it depends on the matrix, right? You need to actually scan the values of the entries and then scale them and then have it then perform the correct row operations based off of those multiples. So there's probably ways you can get around it. But in terms of like a pure algorithm, I think this method we just did might be a little more straightforward. The other reason that it's useful is that sometimes we have matrices that actually have functions in them. You'll see this a lot in differential equations, which I imagine a lot of you guys have to take. I know all the astrophysics people are going to have to take it. I know we have maybe one economics person. Economics, honestly, if you get differential equations in economics, you will blow on some economists because they're not going to know that stuff, but it's huge for mathematical theories. And so differential equations, you often, partial differential equations in particular, you will come up with like Jacobian matrices. So you've seen a little bit in Calc 3, if you've taken Calc 3, where our Jacobian matrix is the determinant of the derivative matrix. And so you have functions within the matrices, and you might have to compute a determinants, or if you need to compute the inverse of the Jacobian, doing the transformation in reverse, you might have functions inside the matrix. And if we have functions inside the matrix, how do we row reduce? Much harder. You can't just take a scalar multiple of 1 times another. You would have to take a function multiple times 1 row plus another, right? You can't necessarily get constant functions in there. And so since functions themselves aren't necessarily invertible, it's going to be hard to just append by an identity and get ones in there. It's not necessarily doable. So if you have a matrix of functions, you can go through the same steps in computing it. Let's see. So we only have about 20 minutes. I don't want to do this. I'll leave it to you guys. Using our formula. This one will be a little bit easier using the formula, of course, because we've got all these zeros in there. So check that one on your own. It's also in the book. It's a good example, though, and it will lead us in a little bit into once we get into spectral theory, which will start tomorrow at the latest. And the whole idea is really, well, when we have to compute determinants and inverses potentially, it's not as nice. We use matrices as a store of information for the information in different vectors and different coordinates. And so sometimes we have a variable change in there. So this is like a 1-parameter family of matrices. And if we have to compute inverses, well, now we can't row reduce. So that's where these techniques really come in handy, especially now if you want to do this with a computer. Because if you're trying to develop your own computer algorithms that will now not only invert matrices, but matrices of functions, you're going to need a more direct computation for it. So take a look at that. I want to touch base on Cramer's rule and maybe polynomials. Polynomials, I think, is a good one. Not hard, though. Real easy. You guys have been doing it. I know you do it in pre-calc and in calculus, probably in calc 2 as well. But in like a baby form, they don't really directly tell you, hey, we're getting a system of equations out of these polynomials coefficients and then computing a polynomial. Let's talk about Cramer's rule real quick. It's another one of these things where it's almost like if you're just given scalars, it's not really useful. So Cramer's rule states that if we have a square matrix and we're looking for a solution to a system of linear equations where we have the same number of equations as variables, and moreover, we expect a non-zero solution, then, well, we know how to do this if we can compute the inverse of the matrix. And typically, again, we've done it with row reduction, appending by an identity kind of methods. Well, using our formula, we now have a formula for the inverse. And if you look at it closely enough and kind of play around with the multiplication, I'll try to walk through it. I don't want to prove it rigorously since we've already done a lot of computations today. If we want to look at the, say, ith entry on our x vector, so let's get rid of that vector sign, so just x of I. Well, what is that going to be? By matrix multiplication, this is going to be the sum of, I'll write it as aij, so the inverse of matrix A, and we're going to be summing over J. So we're summing down the columns of this guy up to n times bj, which is going to be now 1 over determinant of A times the adjugate of A times bj. Where, of course, bj is the jth entry in vector B, the ith entry in vector I. So, of course, we're going to take the ith column times all of, or excuse me, we're going to take the ith row of A inverse, which means we're going to be summing along the columns and then times the entries of J. So if you kind of just eyeball how that works, right? If we have our A inverse, it's going to be our ith column and then times all of the entries of B. So we're doing that scalar product, that inner product between that row and that our column vector of B to get that ith entry. And now, funnily enough, so since the adjoint of A was formed by a transpose, and because the adjunct of A, each of the entries was a cofactor matrix, was a determinant of one of the minors, you can actually realize that this formula reduces to the determinant of a matrix which the book kind of lists it like this. where this matrix is matrix A. With column I replaced by our vector B. So if you kind of just think about it, well, what's going to happen if we expand this determinant about this column? Well, I'll have B times the B1 times the minor entry of that. So that's going to be the 1 ith minor entry. And because of the transpose, if you kind of think about it as a transpose, or the way that we use the transpose to make the adjoint, sort of summing along this column will actually give us that sum along the rows that we kind of see in this formula. Take a look at that for the breakdown, or just try to make sense of why that's true from the book. I don't want to go through it now since we don't quite have time to really rigorously do that. But that's kind of the idea. If you kind of just think about, well, what's this adjoint, or what's the ijth entry here? Well, because the adjoint is a transpose, it's really the cofactor of ji, which is what you would get if you start with the original matrix and expand upon a column, replacing your bj or your b entries with that column. So, example. Why is this useful? Essentially what it says is, if we're trying to solve a system of linear equations, well, we've seen a couple methods now. Like, of course, if I can compute the inverse and throw it over there, we're good. We just saw the method we learned to compute the inverse isn't necessarily the nicest. It seems to take a little more steps than just doing the row reduction. And even row reduction takes quite a bit of steps, at least 6 to kind of get these 6 entries as 0, possibly a few more if we have to scale or switch rows. But now essentially what it's going to say is that our x is going to be the determinant of a1 over the determinant of a. So this, again, it's a nice, direct, straightforward algorithm. Like, we can just program a computer to compute determinants all day. And determinants with Laplace expansion, then again, it's very straightforward. There's no like choice in our operations with this type of formula. Whereas if we row reduce, again, we have to choose what row operations we're doing next and how we process our row reduction. So it's a little less straightforward, a little harder if we wanted to program a computer to do it. So in all of these, we're going to need the determinant of A. So let's go ahead and compute that guy real quick. So we've got our A is 1, 2, 1, 3, 2, 1, 2 minus 3, 2. And so I'm going to do a few row reductions. We're going to go to 1, 2, 1. I'll take minus 3 times the first row plus the middle row. So that'll give us a 0 there, a -4, and a -2. Minus 2 times the first row plus the last row. So that'll give us a -4, -7, and then 0 here. And then so from there, I'm just going to compute. We're using some bad notation here. Be careful with your notation. This A1 means we're replacing matrix A with our B in column 1. Of course, I was using A1 and A2 in the last problem to just denote the different matrices obtained at different steps. We'll just call this matrix B. And since we did row operations of type 3, same determinant. And so our determinant of A equals determinant of B, which we can now do as 1 times the determinant of -4, -2, -7, 0. And that's easy enough to compute without having to do any more row operations. And of course, if we're expanding upon the first column, the other 2 minor matrices will have a 0 out front multiplied them. So we don't need to worry about those. And so what are we going to get here? 1 times 0 minus 14. So we get 14. Negative 14. Did I do that right? Just to double check. -3, -6, -4. -3, -1, -2. -6. Did I do that one right? No, -4, -3. Yeah, okay. So we get -14, and then now we want to check A1. So we simply replace our first column, 1, 2, 3. So it was 1, 3, 2. We're replacing it with 1, 2, 3. 2, 2 minus 3, 1, 1, 2. And we need to compute a determinant again. So let's go ahead and do some row reductions. We've got 1, 2, 1. We'll do -2 to get rid of that guy. So this will be -2 and then -1. -3, we'll get a 0 there. And then -6 minus 3 gives us -9. -3 plus 2 gives us -1. And so we'll call this B1. Row operations of type 3 don't change our determinant. And so that's going to give us a 1 times the determinant of this guy. So +2 minus +9. So that'll give us a -7. And so our x is going to be -7 over -14. Which is 1/2. So that is our x. And then we could do the same thing for y's. Now that we have the determinant of a, we don't really need to compute that again. We can keep that. So we would compute our y. Is just going to be the determinant of A2 over the determinant of A1. And so it's going to come down to computing R1, 3, 2. Now we're replacing column 2, 1, 2, 3, and 1, 1, 3, 1, 1, 2, excuse me, with our A2. And again, computing determinants might be easiest to doing some sort of row reductions. I'm going to do it a little different. So we've got 1, 1, 1 in the first row. I'm going to do minus row 1 plus row 2. So that'll give us a 2 here. That'll give us a 1 here and a 0 here. And then I'm also going to do now -2 row 1 plus row 3. So that'll give us a 0 here, a 1 here, and a 0 here. Why did I do that? Well, actually, if you kind of generalize, our process of finding determinants becomes much simpler when I have a lot of zeros in a given row. So really all we need is a lot of zeros, either in a row or a column. So you could even use column operations if you want. Again, as long as they're column operations of type 3, if I wanted to add 3 of column 2, column 3 plus column 1 or something like that, not going to change the determinant. But now that we have this row of zeros, we can say that the determinant of A2, of course, it's going to be the same as this guy. And so if we expand upon our last row, so that's going to be 1, 1, 1, 3, positive coefficient times our positive 1, now times the determinant of 2, 1, 0, 1. So now this minor. So 1 times 1, and that's just going to give us 2 minus 0. So that one's not too bad. So very direct with Cramer's rule. It is unfortunate that the nice thing about row reductions is you kind of get all of the solutions at once, right? Once you finally row reduce, or if you're clever and use LU factorization for a system of linear equations, once you find one answer, you essentially have all of the others. They're almost immediately given to you. Cramer's rule, good for picking out one solution at a time. And again, very straightforward. Of course, we're using row reductions to help us compute our determinants. But if we had a computer, computer wouldn't need to row reduce, right? A computer could just compute a determinant very quickly and very directly. I'll leave it to you guys to check Z. So solve for Z, and then maybe you want to check that. Plug in your X, Y, and Z that you find into this equation and see if it holds. Of course, the other nice thing about Cramer's rule now is, again, if we have matrices now with functions in them, and we're really trying to solve like a system of equations or a system of functional equations, maybe where the functions are just one parameter functions depending on t, then row reduction isn't quite going to work. And so having a direct algorithm to compute those is going to be much more efficient and much more doable, since a lot of functions you can't compute functional inverses. Okay, so we've got 10 minutes. Let's do one more example. On the exam, so I do want to test over Cramer's rule. Like, again, if I have a general question, like finding the solution of a general system of linear equations, I don't like the questions that like force you to do it by a certain method, you know, because in your working careers, wherever you end up, even if it's just in higher math classes, typically if you have problems like that, you just need to solve the problem. You don't need to follow a specific method. So general, if it's solve a system of linear equations, you can use whatever method you want. However, since this week we are learning about these applications, I do want to be able to test, you know, Cramer's rule. So I don't know how specifically I'm going to do that. It might just come down to a fact of like, you know, solve the system of linear, given a system of linear equations, solve for the x coordinate. Right? If you're solving for just one coordinate, maybe Cramer's rule is a bit quicker. Or I might say something like compute the determinant of A2 and A1, or I could give it in parts. It might be a good Cramer's rule type problem. Sorry, this shouldn't be A1. But like, you know, first part, compute the determinant of a matrix. Second part, compute the determinant by replacing the constant row with whatever corresponding row. And then, of course, the last part, what should that value correspond to by Kramer's rule. So something like that. You should know Kramer's rule, but I don't think I can make the question too terribly difficult as long as you understand the process here. So let's just kind of end with something easy. So polynomials, everyone knows, are of the form something like this, where our constants a0 to an are being multiplied by corresponding powers of x, x to the n, x to the k. And notice that a polynomial of degree n is uniquely determined by n plus 1 coefficients. So since we have that constant coefficient, there's one more coefficient than the number of degrees. So for example, if we want to solve for a polynomial that passes through a given number of points, we can actually set this up as a system of linear equations for the coefficients. So for example, if we want to find a polynomial through points 1, 2, let me make sure I get these points right. Sorry, 1, 4, 2, 9, and 3, 12. Well, if I have 3 points, we need at least a degree 2 polynomial. There could be degree 3, degree 4 polynomials that will for sure pass through these 3 points, but they won't be unique. So our best approximation is to use a quadratic. We know that there is going to be one and exactly one quadratic function that passes through these 3 points. And so how do we get that? We have y is equal to a0 plus a1x plus a2x squared. And all we have to do is plug in the points, and what are we going to get? We're going to get a nice system of linear equations. Uh, 2a1 plus 4a2. And if we plug in our last points into our generic equation, 12 is a0 plus 3a1 plus 9a2. In other words, to solve for the exact degree 2 polynomial, we need to solve a system of equations for our coefficients. So we've only got a few minutes left in class. I don't really want to go through this since we've just done a lot of computations, and now since we've reduced our problem down to solving a system of linear equations, process is the same, solving the system of linear equations. So hopefully this problem, it looks a little familiar, hopefully. Because we've done problems like this. I know we give problems in Calc 2 where it's like find the quadratic that has a certain max and a certain x coordinate intercept or something like that. Or sometimes we say, you know, find the degree 3 polynomial with this factor, and then that passes through a specific point. Usually in Calc 1, Calc 2, pre-Calc even, we're really only given maybe a degree 1, or sometimes we give you one of the coefficients if we're looking for a quadratic. Now, since we're in linear algebra, you can do it for any degree polynomial. So you can find, you know, even 4 points. Now we just have a 4x4 matrix to solve the cubic equation that would pass through those 4 points. And we can do that with either our row operations, you could use your inverse matrix formula, or you could use Cramer's rule if you want to solve this guy now. Or good old LU factorization. Any questions on this? I may put a question like this on the next midterm. It'd be at most 3x3, I think, especially if you have to do all the steps. But I may not, because again, if you know, I think a lot of you guys, myself included, if I were to try to solve this, I'd probably just use row reduction, especially because the coefficients aren't terrible, and it'd be pretty easy to row reduce this guy. So I would just use row reduction, and if the typical standard method is row reduction, there's not a real good reason to test on it in this exam. So this exam, we want to test on the newer material. But we'll see. I'll let you guys know as I get it written in the coming days. Any questions?